is that there are three terms we need to be concerned about. In our GARCH and ARCH equations in models, we have residual, we have squared returns y equals to u square, or we can say variances square of the variance v. So basically y equals v. We are concerned with v, and v is our output variable or response variable, right? Or the dependent variable, the variance. So we have v squared indeed, and then we also had we had sigma square, and sigma square represented we represented sigma square in the programming code with h, which meant our GARCH or the ARCH model. So first there's a relationship with y and v, so y square was v square as second term in the ARCH model, and then the GARCH representation. There's another relationship that we also needed to remember, which is well, we could have presented instead of going through a very difficult log normal model, we can simply normalize or standardize our GARCH representation in y by simply multiplying the square root of the GARCH estimation, which is sigma square, with z, standard normal distribution, and the y we had would be a normalized GARCH representation. Now we're going to talk about integrated GARCH. And a feature of the volatility of GARCH 1-1 model of equity returns is that the second element, which was the ARM element, alpha 1 plus beta 1, was equivalent to or equal 1 for all the indexes. And it is suggested that the volatility series, because they are equal to or equivalent to 1, they have a near unit root, and the GARCH models with a near unit root is referred to as I-GARCH model, where the I stands for integrated, following the discussion of non-stationary models. Integrated GARCH model. One way to proceed in estimating an I-GARCH model where the estimation is near unit root is to impose the unit root restriction. So we can impose an unit root restriction. In the case of a GARCH 1-1 model, the restriction is alpha 1 plus beta 1 equals 1. We specify it very specifically, and in which case beta 1 is replaced by, obviously do an equation solution, beta 1 equals 1 minus alpha 1. So we simply, in place of beta 1, we simply put 1 minus alpha 1, and hence, wow, so the first parameter and the second parameter. The second parameter, the control parameter for the GARCH part, changes to 1 minus alpha 1, and the conditional variance in the equation becomes as it is before, just with 1 minus alpha 1. And now the log likelihood function is maximized with respect to the variance parameter alpha naught and alpha 1, with the estimates of beta 1 is obtained after the algorithm has converged. From Slutsky's theorem, this estimator is also a maximum likelihood estimator. Moreover, from the invariance property of maximum likelihood estimators, the alternative strategy of substituting out an alpha 1 and maximizing the log likelihood with respect to parameter. Okay, so if I take out alpha 1 and just after that again I do substitution, so instead of doing 1 minus alpha 1, if I do 1 minus beta 1, I guess I get similar and identical property parameter estimates. So basically, estimating with respect to beta 1 will give me same results from the invariance property. So I can estimate the model with 1 minus alpha 1 and I replace back to beta 1 from Slatsky's theorem. It is the same thing from invariance property. If I just maximize directly without beta 1, that is also fine. A generalization of iGARCH model is the fractional integrated GARCH model FIGARCH proposed by Boleslav, Michelson and by Lee. So a generalization process is FIGARCH. The FIGARCH model has 1 D1. Remember that. So the parameters are 1 D and 1. So D is an important parameter here. Alpha naught 1 minus beta 1 L. So basically we have alpha 1. Instead of alpha 1 we are taking 1 minus beta 1 and we are taking the lag parameter. So 1 minus beta 1 L minus 1 minus alpha 1 L minus beta 1 L, 1 minus L to the power D divided by 1 minus L. V square plus beta 1 sigma square 1, where 1 minus L D is J0 to infinity. Gamma function tau j minus d tau. So this is a difficult equation. df j plus 1 is the gamma function. This model is equivalent to GARCH 1 infinite model, where the infinite lag on the arch component is fully parameterized in terms of alpha 1 beta 1 and the fractional differencing parameter d. The iGARCH model is a special case occurring when alpha 1 beta 1 1 and d equals 1. So d has to be 1. But if we need to estimate a phi-GARCH model, we need to start values of v squared to begin the recursion. To allow for long memory in the conditional variance, a common choice is to start with the lagged variances up until 1000, the sample variance of y. So this is a bit difficult. We'll try to see this when we face this, okay, how we can implement. But generally, so we were still in this problem. We skipped the iGARCH function. So now, as we know, we can do iGARCH function. So obviously log likelihood equals mean minus half log minus mean log of LT by. So log 1 is log LTI by, and log LT function will return us log LTI. So this is the function neg log I. Probably I'm gonna call neg log I, yeah, and it will use log LTI. Log LTI by, okay, is this function log LT. Here is also that is true. I get a bit confused all the time. So neg log I is my function, by parameters. So it will estimate log LT, which is the mean of log LTI by. Log LT will come later, and it will return the log LT. And now log LTI is coming, the function of by. Again, parameter b is absolute value of b, t is length of y, obviously u and y, and obviously h is standard standard deviation of y square. Okay, the variance, we are finding the variance multiplied to ones, okay, so that the first one is fine. So in 2 to t, up to this is fine, and then instead of, what do we do? Instead of beta 1, we do 1 minus beta 2, hi minus 1. That's all the thing that we needed to know. Everything else remains same. We jack in the iGARCH into our log likelihood, regular log likelihood function, u divided by square root of h squared. So this is the model, and then we call for this beautifully in our problem. In iGARCH, estimating the iGARCH, we start with a parameter, estimated parameter 0.5, 0.9, because we have 2 parameters here, not 3. So if just like arch, our GARCH will start from 0.05, 0.9 iGARCH. Yeah, because we have only alpha naught and alpha 1 to estimate. And then we just do the regular thing that we always do. Neg log I, call for the function, by method vfjs, results are found. That's all. Very simple. Okay, so we were talking about phi-GARCH and additional variables. Now let's get back to our theoretical discussion. Alright, so what are the additional variables? A further extension of the GARCH class of model is to include an additional variable in both the mean and the variance. Okay, and I'm not sure if I can include okay, no, here I cannot include my video. It's to include additional variables in both the mean and the variance. An example using the GARCH 1 conditional variance specification is y equals gamma naught gamma 1 xt plus vt, 0 mean sigma square variance, very important. GARCH 1 specification indeed, right? And obviously you have the vt thing, fine, where y equals vt and sigma square is the GARCH parameter. Okay, this is an additional variable. Now I'm adding another variable. I have a GARCH 1, but gamma wt is being added. So gamma wt and gamma 1 xt is what is the difference from previous discussion, where xt and wt are additional explanatory variables which are important in explaining the mean and the variance respectively. So this explains mean, this explains variance. Gamma 1 xt will give us mean, gamma wt, gamma, what is called sigma and gamma, sigma 1 xt and no not sigma, delta I think, right? I completely forgot. Anyway, I'm sure this is gamma and this is delta. Okay, so which is important in explaining the mean and the variance respectively. Examples of omega t include straight volume, policy announcements, day of the week and holiday effects. So these are shocks which is affecting our GARCH or variances. Hand-and-Park allow for non-stationary variables in the variance to model the GARCH properties discussed earlier. Okay, so the next exercise is talking about non-stationary variables in the variance to model the GARCH property. So we're gonna have non-stationary variables and see how the GARCH property is changing, which is we have talked about up to 5 R's and an H. The exercise is based on Hand-and-Park, who modeled the GARCH non-stationary conditional variance, using non-stationary variables. So non-stationary conditional variance is being modeled. The data consists of S&P 500 stock returns, YT and the interest rate spread between these bonds, blah blah blah. Omega t are recorded monthly, weekly and daily. This is the additional explanatory variable. So first we have the regular GARCH model and sigma square. Consider non-stationary GARCH model. So the non-stationary model is being added. It's not stationary, GARCH and NH, which gives me an additional equation, which is sigma square is alpha 1 v square minus 1 plus gamma 1 omega t minus 1 to the power phi. Something new. Alpha 1 v square minus 1 gamma omega t minus 1, right? And this is the model actually, because obviously this is the squared return, not a big deal. Okay, this is what we always had, y equals v, so fine. But this is the additional term with my GARCH model, so this is not GARCH, so the third element is not present here, but an explanatory variable is present, where omega t minus 1 represents lagged spread of non-stationary variables. Non-stationary variables, lagged spread. Estimate the parameters, okay, by maximum level for monthly, weekly. Test the restriction, phi equals 1, so restricting. Then GARCH, we extend the model. Again we can do it, perform a word test for restriction. Okay, this is interesting. Let's see a GARCH H model and how Mr. Han and Park do it. I'm gonna pause the video now, prepare the stuff, then I'm gonna come back. So the importance of what example we are going to practice here is manifold. First of all, we're going to look into FI GARCH, not only iGARCH, which is the unique root on GARCH, but FI GARCH actually is generalizing our GARCH iGARCH model, right? And then we know in FI GARCH we have an additional element lambda omega t minus 1, and that allows for different items to be included, like day of the week effect, or in this particular paper, in this particular work, the authors included non-stationary non-linear models, like the ARCH autoregressive model is a non-stationary model here, ARCH model, conditional heteroscedastic model, and we are using non-linear models, which is very highly used and very interesting inclusion in this particular program. So let's see how this program works. So one more time, I'm gonna quickly talk about what is expected from this expected from this particular program to learn. We are not learning only an FI GARCH here, but also an additional variable, which is lambda omega t. And omega t can be included as any of the shocks. What do we do in GARCH? In GARCH we see how longer a shock will persist on the variance of any variable, right? How quickly the shocks will adjust, or how long the shocks will last. However, if there is a policy announcement, which is a shock or a day of the week or a holiday fact on our variances, how will that sustain in the variable of interest? And FI GARCH as an additional variable will help us generalize our iGARCH, and so that is what we are gonna do here. So very interestingly, first of all, indeed we need a function for our GARCH 1 model, and just like before, we have b, we have t, obviously we need u, mean, because we are talking about an here we are talking about iGARCH. So instead of beta 1, we have alpha 2, which is y minus beta 1. We studied that before, right? So u equals y1 minus alpha 1, or the residual. Basically, you can explain it another way: y minus the variance, because y minus the forecast error. Y minus the forecast error, because the forecast error is basically the actual value minus the equals y minus variance, right? So what was the forecast error? I'm just gonna quickly go have a look. Kind of slightly lost it here. So y square minus sigma square, right? So E here, y square minus sigma square, beta 1 is the sigma square. Exactly, that's what we are doing, right? So that is it. And then obviously, just like before, we have estimated our variance sigma square, which is y minus beta 1, and then H is our GARCH model, and then we have the regular GARCH estimation. So generally y is u, but here y minus beta 1 is u, and beta 1 is 1 minus alpha 1. That is a reason for 1 minus beta 1. That is an explanation for 1 minus beta 1. Or we can be thinking it in terms of y square equals sigma square plus e, and we're interested to find e. We're representing this term with e. So but that's not sigma square, is the variance, right? So basically is the variance y minus beta 1. Fine, I'm fine with that, no problem. So let's get back to our iGARCH example, integrated GARCH. Oh yeah, I'm really sorry. 1 minus beta 1 is because alpha 1 plus beta 1 should be equivalent to or equal to 1. And so our beta 1 is 1 minus alpha 1. And that's why y minus beta 1. And this is a constraint we are putting on our equation, so that we have this model alpha, because we're gonna this is the first parameter, right? This is the first parameter, that's why 1 minus alpha 1, so that we can get this unit root situation, because it's a GARCH. That's the constraint we are putting on our model. And then regular GARCH model, again fine. So this is the only constraint that we are putting on our model, except that everything else remains as it is. Then comes GARCH Hurn H model. Okay, and GARCH non-linear heteroscedastic model. And kind of like machine learning, this is very important because we are gonna forecast non-linear models. That is our objective from this course. So again, 1 minus beta 1, alpha plus beta 1 equals 1. From this is coming. And if string comparison, which means earlier we just used a flag against numbers, now we're gonna use flags against string variables. And so we're gonna in R is easy. You don't have to differentiate, you don't have to pass this into any function. Flag equals arch. But in MATLAB it's different. So string comparison, flag arch. If we are passing arch, then we put this in a for loop, but then we need two conditions under for loop. So if there is restriction, we have b3 absolute value of omega 1 from our problem number 5. Yeah, it was the equation omega 1. So if there was a constraint or a restriction, if restrict, then we're doing string comparison here actually, so it will take the string. So if we pass restrict, then it will not do everything, it will just take obviously the arch part, alpha 1 v square, and omega b3 absolute value of omega 1. But otherwise, if it is not restricted, then it will be multiplied to lambda. So beta 2, beta 3, beta 4, right? So oh no, we are talking about GARCH model. All right, so this is the additional term. Yeah, additional term omega phi. So this is phi, right? To the power phi, yeah, beta 4. So and phi is the restriction, because we test the restriction with phi equals 1. So first, if restricted, phi is 1. If not restricted, there is a value for phi that will be estimated. Very simple, from the same equation of GARCH 1.1 model, ARCH 1.1 model. And so for then if else if like that, so here we are generating two vectors. One is a restricted vector, one is the unrestricted vector, with for loops and with if function. Putting the for loop under the if function, we are basically creating two flags. So string comparison flag, string comparison flag 2 to t if restricted, which is if I equals 1, then this is our equation, absolute value of omega 1 I, and if not, then we just square with our phi. And if function ends here, also the for loop ends here, else if our flag is GARCH, if our flag, there is an error here, if there should be second bracket beginning here, flag is GARCH, then I equals 2 to t, I in, so you see I in 2 to t, I in 2 to t. So for GARCH we just have the second component added here, b2, then b3 y minus 1 square, b4 hi minus 1 so what else? Yeah, we have the intersect here for GARCH that was missing, and then because this is GARCH model, so alpha naught is here, there is no alpha naught, but alpha naught is here as well as alpha 1 beta 1, everything is actually the equation increases h. So then we do not ask it to, then the equation ends here. As soon as the equation ends, otherwise display wrong flag. So with this we have basically estimated 4 vectors with this function, and then we find our log likelihood function. So this is the function, and then let's apply these on our data. So we are taking daily data, frequency on a daily basis, and there are 3 frequencies: daily, weekly and monthly. Again, after the data has been loaded, we are doing string comparison, and if frequency is daily, we are taking the spread for the third and the fourth column spread. So what are the information that we have? Basically we have the data is stock returns, interest rate spreads between 2 types of bonds, triple and triple B bonds. So we have the bond spread and the returns of the equity from third column and the fourth column. If string comparison frequency is daily, so we are taking the variable daily data, for which we are taking the third and the fourth column. So there are 3 different variables: daily, weekly and monthly structure is there from our actual data. Okay, fine. Otherwise, if frequency is weekly, then the data takes go to weekly data and takes the third and fourth column of weekly data. Otherwise it takes third and fourth column of monthly data. So it depends on what data we have, alright, and depending on that, otherwise there is wrong frequency. So now let's define the variable. Trimmer returns and spread y is equal to yt minus 1, or yeah, yt is as it is, current present value of yt, and the past value of omega, which is t minus 1. Lag spreads, not in percentages. So that is then we estimate GARCH model. We initialize our model with random numbers, we create a column in R, and then we simply do an optimization to find the GARCH models. Theta LF1, fn in search, because remember we have string comparison, so fn in search. Okay, equal for the GARCH model. Fine, there's no well, twist in the GARCH model, is as simple as that. We have alpha, not alpha 1, so we have all these variables estimated. But what for our non-linear model, for our or GARCH, so if string comparison, again we're gonna start a if function. If string comparison flag is arch, then call for the neglog NNH, which was, yeah, log likelihood function. So see, there's a lot of logical function in this program, but quite simple. Implementation is quite simple. And so if string comparison flag is arch, then we call the function and vy omega arch 0. What was our what was the function actually? How many parameters we pass? Vy omega flag restrict. So because if any search, because there is flags vy omega flag 0 start and ops, fine. So y omega flag restrict is f, y omega flag equals flag. So these are all the parameters that the R program takes. Restrict is false. Method neldermid, so this is new. Method is different. Neldermid method, not BFGS. Neldermid method is being used. We are restricting. Restriction is false. We are not restricting. We initialized, but we want the system to find y1 omega GARCH system to find the value of phi, because either restrict will be, no, restrict is always false. Okay, so this is the first one we're talking about, where phi equals 1. With phi equals 1, 0, 0.2, 0.5, 0.1. So gosh, we have all the different parameters. Oh no, I went down a bit too far. Okay, 0.2, 0.5. So restrict is true. We are restricting. I'm sorry, restrict is true, and BFGS. So neldermid is being used for what? I missed it. Oh, for arch. No. When there is restriction, we are doing neldermid method for arch. Here is also, that is true for arch. Phi equals 1. Okay, so that is how we are just simply flag is, when flag is GARCH, we are estimating. Again, with phi equals 0 and phi equals 1. That's all. We are estimating too. There's just one new thing we learned, that we use neldermid method earlier, estimating our arch models, not GARCH. When we were estimating our arch models, GARCH and NH, if flag, let's see, if flag arch. Okay, so we use neldermid method here. I'm not sure what an neldermid method is. Never used it before. This is the first time we are using it. Okay, I think we'll have to go through it one more time, so we'll do it later.